Welcome everyone to part 5 of my series of presentations about the best methods for converting aldehydes into secondary alcohols. This video is about catalyzed aldol additions of aldehydes to ketones. By aldol addition, I refer to reactions between enolates and aldehydes that yield secondary alcohols, whereas aldol condensations generally refer to reactions between enolates and aldehydes that yield alpha-beta unsaturated ketones. Aldol additions can in principle take place without any catalyst, as shown here, but for most aldehydes and ketones this reaction is too slow. Highly electrophilic aldehydes, however, such as glyoxylates or chloral, may give good yields of aldol addition products just upon heating, without the use of any catalyst. Aldol additions can be catalyzed both by acids and bases. Most ketones contain only small amounts of enol, and reactions where the enol is consumed, such as the halogenation of ketones or aldol additions, can be catalyzed both by acids and bases because these increase the rate of keto-enol tautomerization and thereby the rate of enol regeneration. The addition of acids does not necessarily change the equilibrium concentration of enol. It only provides for the rapid formation of new enol if consumed by some reaction. Acids also activate the carbonyl group of the aldehyde. Of course, acids also increase the electrophilicity of ketones, but aldehydes are usually more electrophilic than ketones and react as electrophile in aldol additions. Usually, aldol additions are catalyzed by bases. Although I've sketched here a metal hydride as base, weaker bases such as sodium hydroxide or tertiary amines can be sufficient to increase the rate of aldol additions by formation of ketone enolates and by increasing the rate of keto-enol tautomerization. Catalytic amounts of bases will also convert enolizable aldehydes into enolates, but these are not very nucleophilic, and it is usually the ketone enolate which reacts as nucleophile and the aldehyde as electrophile. Catalyzed aldol additions are being conducted on a huge scale because almost no waste is formed other than the catalyst, and the starting materials are readily available and inexpensive. These reactions are also easy to perform and sometimes even do not require any solvent. Furthermore, enantioselective variations have been developed which enable the low-cost preparation of enantiomerically enriched secondary alcohols. The main disadvantages of this kind of chemistry are that beta-hydroxyketones readily eliminate water and that a number of other reactions can occur too and lower the yield of the target product. This is an example of a purely thermal aldol addition. No catalyst was required because the aldehyde, ethyl glyoxylate, is extremely reactive and reacts with enols much faster than less electron-deficient aldehydes. The secondary alcohol did not eliminate water because the resulting olefin would be 1,2 substituted with 2 electron-withdrawing groups, what is energetically unfavorable. All kinds of nucleophiles usually add quickly to such electron-deficient olefins, including water, and the preparation of such olefins therefore requires higher temperatures, catalysis, or more aggressive water-removing reagents. In this example, the aldol addition was brought about by a mixture of the Lewis acid magnesium iodide and the weak base diisopropylethylamine. A high yield of the aldol addition product was obtained. Such products are, however, quite unstable and readily eliminate water. This is a further example of the use of a mixture of a Lewis acid and a base to promote aldol additions. To prevent aldehyde enolate formation, the ketone titanium enolate was prepared by stirring a mixture of the ketone titanium tetrachloride and tributylamine at low temperature for 30 minutes. Only then was the aldehyde added and the aldol addition proceeded with high diastereoselectivity and yield. Because titanium enolates are mostly formed as C isomers, and because titanium can form a bond to the aldehyde oxygen atom, the addition proceeds through a closed transition state, what can provide a high degree of stereochemical control. Here, the pre-anti transition state entails steric repulsion between the aldehyde alkyl chain and the ketone, what led to a preferential formation of the syn isomer. Another strategy for diastereo and even enantioselective aldol additions is the use of amino acids as catalysts. In particular, proline can sometimes promote aldol additions with amazing stereoselectivity. In this example, the product was obtained in high chemical yield but also with high diastereo and enantioselectivity. It is assumed that these reactions proceed by intermediate formation of an enamine from proline and the ketone, which then adds to the aldehyde. Although the aldehyde is more electrophilic than the ketone, it will only form an aminal reversibly, but neither an enamine nor an iminium salt upon reaction with proline. The reason for this is that the enamine would be a bis-donor-substituted ethylene, which would be very nucleophilic, sensitive toward oxidation, and energy-rich, and is therefore not formed. The iminium salt would be strongly electrophilic and energy-rich, its electrophilicity being further increased by the electron withdrawing effect of the other nitrogen atom through sigma bonds. Therefore, it is not formed either. In this example, the aldehyde did not have any heteroatom in alpha position. Treatment with 10% of proline and a large excess of acetone yielded a mixture of the product of aldol condensation and aldol addition, the latter with modest enantioselectivity. On the basis of some control experiments, the authors concluded that the condensation product was formed by reaction of acetone with an aldehyde-derived iminium salt, followed by beta elimination of proline. The secondary alcohol, however, was formed from an acetone-derived enamine. Proline catalysis usually gives better results with non-enolizable or alpha-branched aldehydes, a large excess of ketone, and in chloroform as a solvent. Unfortunately, quite a number of side reactions can interfere with catalyzed aldol additions. The most prominent is of course aldol condensation. Most 3-hydroxyketones eliminate water readily, both under slightly basic or acidic conditions, and forcing reaction conditions will usually only yield alpha-beta unsaturated ketones. In the example on this slide, despite the small amount of base and mild temperature and the fact that the alkene formed was electron deficient, extensive elimination of water occurred. Even if an excess of ketone is used, as in this example, some metal cations can promote multiple aldol additions through chelate formation. In this instance, the aldol addition occurred twice and at the same carbon atom, despite the huge excess of acetone. Forcing conditions do not only cause the elimination of water from the initial aldol, but can also promote Michael additions. In this example, the ketone underwent Michael addition with the initial product of aldol condensation and then a further intramolecular aldol addition to yield a tricyclic hydroxyketone. In the presence of bases, aldehydes sometimes disproportionate into acids and alcohols in the so-called Cannizzaro reaction, or into esters in the so-called Tishenko reaction. Therefore, when using strong bases to promote aldol additions, some hydride transfers may also occur and yield unexpected esters of 1,3-diols or the unesterified 1,3-diol. Enantioselective versions of this reaction have also been reported in the given references. Here are some more examples. In particular, enantioselective aldol additions catalyzed by some small organic molecule have been intensely investigated in recent years. The weak point of many of these procedures is that most products are so unstable that they can only be used as synthetic intermediates, and great care must be taken to prevent racemization by an elimination addition mechanism. The next presentation is about the stoichiometric formation of ionic enolates and their reaction with aldehydes. Less side reactions than with catalyzed aldol additions are usually seen with stoichiometric enolate formations, and the outcome of these reactions is generally more predictable.